Great. So hello, everyone. My name is Kacper Jancewicz. I represent University of Wrocław, Poland, and on behalf of my co-authors, the whole research team led by Professor Piotr Migoń, I would like to talk today about high-resolution geomorphometry, treated as a tool for a better understanding the genesis and contemporary processes in sandstone landscapes. And you might ask a question, why the sandstone areas? Because they represent a very distinctive type of structurally driven relief, and fine examples of such can be found in Central Europe, with such specific landforms as dissected plateaus, isolated tabular hills, canyon, joint-controlled cleft and valley systems, and also smaller yet numerous convex forms like tors or boulders. And you can see them on the photos on the right side. And yet for many years, these areas hampered quantitative relief studies and kind of remained outside of mainstream of research. And things have changed over the last decade, mainly due to development and increasing availability of high-resolution LiDAR-based DTMs, which in turn have brought a gradual growth of scientific interest in sandstone geomorphology. So, starting without an established set of morphometric measures dedicated for such type of landscape, during the last 5 years, we managed to tackle quite a broad palette of topics concerning sandstone landforms and geomorphological processes in few different locations, and thus I would like to share some our experience with you. So today's topics are, firstly, main issues with airborne LiDAR data, which we had and still have to deal with, and why? Because we see the matter of the quality of the elevation data as fundamental in this particular case. And secondly, I will present 3 examples of using the morphometric indices in geomorphological research in sandstone areas, as you can see below: morphometric features of tabular hills, diversity of cleft and valley systems, and drainage connectivity patterns. And the first issue, I like to call these issues critical because I feel they are really, really important for us. The first one is due to location of our study areas, which are, as you can see, in 3 different countries: Czechia, Poland, and southeastern Germany, Saxony. And this means that we have to work with 3 different LiDAR datasets, DTM products ready to use, or corresponding point cloud data, and they are of different quality. You can notice differences in density of the original point cloud, which is quite low in case of Czech data and quite high for the German dataset. And so right from the start, it causes difficulties in conducting any comparative study of landforms which are of the same type and yet are located in 2 neighboring countries. And for instance, one can expect huge differences in quality of digital representation of such features as steep rock walls or some narrow clefts, as surely the density of which is less than 2 points per square meter is insufficient. And the second issue is linked with the fact that in Central Europe, our sandstone areas are usually densely vegetated. You can see it on this location map. They are marked by red polygons. And I guess we all know that tree canopies can greatly decimate the number of ground points from the airborne LiDAR data. But we asked ourselves to what extent it actually does happen in our case. So we tried to check it out, and basing on the 3 sites, each site of square shape, 4 square kilometer area, and at least 2/3 of this area is covered by forest. And these sites are presented on the left figure. And on the right, you can see plots of ground point density regarding non-forested, sparse forest, and dense forest conditions, also the dominant leaf type. And results show that in dense forest, the ground point density can be even 2 times lower comparing to the open space, pasture or grassland. And also, you can see the fact that forest areas of predominantly broadleaf species are the ones of higher ground point density, if only LiDAR data were acquired during a leaf-off conditions, which is not the case of the Site 1 in Czechia. And those 2 issues are ones that we have to live with and deal with them. And the third one is, I guess, the only one we can solve. And the third issue is are the DTM artifacts, which are caused by wrong classification of the point cloud. In our study sites, it happened quite often that smaller landforms like tors or boulders are filtered out and treated as non-ground objects, same as trees or buildings. And as you sometimes they are huge ones, as you can see on the photograph on the upper right side. And what's the solution? Actually, there is no universal formula. And here we present an example of dealing with a relatively dense point cloud in the area of Labyrinth Hill in Germany. And to some point it's automatic, but in the end it required manual cleaning up, so it was quite time consuming. But is it worth the effort? Yes, it is. As you can see here on these 2 examples, it's worth to spend some time meddling with the original point cloud, and you can see how many convex landforms can be restored. They are marked by these reddish spots on the DEMs of difference visualization. So if we finally have an input data as close to reality as possible, what's our methodic approach within sandstone areas? We like simplicity. And aside from the basics such as relative heights or slope inclination, we like using tools from Saga GIS software very much, especially these 3, which you can see on screen. The topographic wetness index, which we use to model spatial distribution of potential surface drainage patterns. And the second one is terrain ruggedness index, which we use as an indirect measure of boulder cover density. And the third one is morphometric protection index, an indicator of positive openness, and it highlights very well enclosed areas such as narrow, deep canyons and slots, and is an indirect measure of the fragmentation of the area. And going to example of our work, at first we asked ourselves how to measure and compare tabular hills. We found this question of big importance as these landforms represent very huge variety of sizes and shapes depending on their evolutionary stage. And so if we measure them, and would the result fit to the traditional evolutionary model of such landforms? And while the set of measures is still under development, first experiments which were done 4 years ago resulted following indices which were intended to reflect size, complexity of caprock relief, extent of caprock walls degradation. But it seemed to be not enough, so we tried to survey further on the relations between area and height of caprock and subcaprock zones. And as a result, we were able to propose the reinterpretation of classic Mesa Butte Pinnacle Depth landform evolution scheme. And at this place, I have to admit that even though morphometric properties are quantitative and as such shall be treated as objective, there are moments, especially during the delimitation of particular elements of tabular hill anatomy, which have to be done manually, and they require expert geomorphological knowledge. So if we do them wrong, the results would be also wrong. The second example is cleft and valley morphology, and it's a subject of PhD thesis of my colleague Violeta Poremna, she is working at it. So here I would like to just present how we use morphometric protection index to visualize these systems, and how it's changed along canyon longitudinal profile depicts its morphological changes as the high values coincide with narrow and deep sections. And below you can see the excerpt of visualization of terrain ruggedness index within canyon bottoms. The field work that we conducted on Bromov Cliff Cuesta revealed that it quite nicely corresponds with segments of thick boulder fills. And third and final example, third and final example is the use of topographic wetness index, which was found quite useful for delimitation of zones of predicted surficial flow. And we tested it in various topographic conditions, mesa, Cuesta backslope, escarpment, and here's the example of the twin mesa of Szczeliniec Wielki, Szczeliniec Mały from Stołowe Mountains in Poland. And you can see the numerous disconnectivity sites of the surface drainage systems within the hilltop of the Kacper zone. And this is the map of this closed depressions which cause the disconnectivities. So concluding, I would like to say that any attempt to high resolution morphometric analysis of sandstone landforms, such complex landforms, based on airborne LiDAR data should be preceded with analysis of data quality and at least a trial to detect and solve classification errors. Anyway, the airborne LiDAR data do provide valuable quantitative information, which, however, I must emphasize, it's not standalone. We think that the field work in sandstone area is mandatory. Yet, up to now, using of the LiDAR data has enabled us to tackle such issues as were seen on the previous slides. And plans for the future, nearest future include further development of morphometric protocols supporting typology of tabular hills, which is not completed yet, and as mentioned before, cleft and valley systems. If you would like to dig further on into sandstones, there are some publications you can look at. And right now, I would like to thank you very much. And if you have any questions, feel free to ask.